Section 1, the many forms of energy. A model of the work-energy theorem. When you exert a constant force F on an object through a distance d, the direction of the force you do an amount of work represented by W equals force times distance. This is our work equation from the previous chapter. The work is positive and the energy of the object increases by the amount of work which is equal to W. Suppose the object is a ball and you exert a force to throw the ball. As a result of the force you apply, the ball gains an energy of motion that is referred to as kinetic energy. The energy of motion. The kinetic energy after the work is done is equal to the sum of the initial kinetic energy plus the work done on the ball. Catching a ball. What happens when you catch a ball? Before hitting your hands or glove, the ball is moving, so it has kinetic energy. In catching it, you exert a force on the ball in the opposite direction to its motion. Therefore, you do negative work. Again, the negative here just implies the direction that it is being applied. Now, if the ball isn't moving, it has no kinetic energy. The initial kinetic energy of the ball is positive. The kinetic energy is always positive. The work done on the ball is negative, so the final kinetic energy is 0 because the ball has stopped. Kinetic energy is represented by this equation, 1/2 mv squared, which is the same equation that we used in physical science when you were freshmen. M is the mass of the object, and v is its velocity. Mass does need to be in kilograms, and v needs to be in meters per second. The kinetic energy is proportional to the object's mass, which means a 7.26 kilogram shot thrown through the air has much more kinetic energy than a 148 gram baseball with the same velocity. The kinetic energy of an object is also proportional to the square of the velocity, which means a car speeding at 30 has 4 times the kinetic energy as the same car moving 15. So even though our speed decreased by a factor of 2, since velocity is squared, we have to take that into account. So it's a 4 times difference. Kinetic energy is measured in joules, which is capital J. Here is an example problem to help you get started when you work your problems. An 875 kilogram compact car speeds up from 22 to 44 meters per second while passing another car. What were its initial and final energies, and how much work was done on the car to increase its speed? So we have 2 velocities. It starts at 22 meters per second. It ends at 44 meters per second. The mass is the same for each velocity. Our equation for kinetic energy is 1/2 mv squared. So we plug in everything that we are given. We're going to do this since we want the initial and the final. So initial will be when it's going 22 meters per second, and the final velocity, or the final energy, is for when it's going 44 meters per second. So we plug these numbers into our calculator. And our initial kinetic energy, 211,750. This is our initial. Our final kinetic energy, we're going to use the same mass, but the final velocity And its final kinetic energy is 847,000 joules. So that answers the first question, how much work was done on the car to increase its speed? So the work done is going to be the difference between these two values. That's the energy that had to be added to increase its speed. So I subtract to find the work applied to the car, which is 635,250 joules. Okay, there are 3 problems for you to do on your own. And then we get to the next part, stored energy. Imagine a group of boulders on a hill. Objects such as these boulders have been lifted up against the force of gravity, and they have stored or potential energy. Now imagine a rock slide in which the boulders are shaken loose. They fall, picking up speed as their potential energy is converted to kinetic energy. In the same way, a small spring-loaded toy has energy stored in a compressed spring. While both of these examples represent energy stored by mechanical means, there are many other means of storing energy. Automobiles, for example, carry their energy stored in the form of chemical energy in a gasoline tank. The conversion of energy from one form to another is the focus of many nations' industries and is an integral part of modern life. Money can be a model to illustrate the transformation of energy from one form to another. Money can come in different forms. You can think of money in the bank as stored money or potential spending money. Depositing money in your bank account or getting it out with an ATM card doesn't change the total amount of money you have, it just converts it from one form to another. Gravitational potential energy. We have an example of a person juggling. Do you consider the system to be only one of those balls, then it has several external forces exerted on it. The force of the juggler's hand does work, giving the ball its original kinetic energy. After the ball leaves his hand, only the force of gravity acts on it. How much work does gravity do on the ball as its height changes? To figure that out, we will use h for the ball's height. We will use Fg, which is the downward work done by gravity, and therefore, because it's downward, we have the negative symbol there, which means the work is negative. On the way back down, the force and displacement are in the same direction, so the work done by gravity is positive. MGH here is positive. The magnitude of the work is the same, only the sign changes. While the ball is moving upward, gravity does negative work, slowing the ball to a stop, which is what we've always said. Anything that is thrown has in an instant, the velocity at the very top is 0. That's what it's talking about. On the way back down, the gravity does positive work, increasing the ball's speed and therefore increasing its kinetic energy. The ball recovers all of the kinetic energy it originally had when it returns to the height at which it left the juggler's hand. It is as if the ball's kinetic energy is stored in another form as the ball rises and is returned to kinetic energy as the ball falls. If you choose a system to consist of an object plus the Earth, so we've expanded our system, then the gravitational attraction between the object and Earth is an interaction force between members of the system. If the object moves away from Earth, energy is stored in the system as a result of the gravitational interaction between the object and Earth. This stored energy is called the gravitational potential energy and is represented by U with a little g. In the example of the juggler, where gravity was an external force, The change in potential energy of the object is then the negative of the work done. The gravitational potential energy is represented by this equation, m times g times h. M is mass, g is gravitational acceleration, and h is the distance the object has risen above the position it had when ug was defined to be 0, which essentially is our reference level, which takes us on to the next topic. Height was measured from the place at which the ball left the juggler's hand. We define that as h equals 0. The gravitational potential energy was then also defined to be 0. This is the choice of a reference level. The potential energy reference level, which is at which the potential energy is defined to be 0, and it is completely arbitrary, which means you can make your reference level wherever you want. Okay, an example problem using gravitational potential energy. You lift a 2 kilogram textbook from the floor to a shelf 2.1 meters above the floor. What is the book's gravitational potential energy relative to the floor? So we are going to use our mass is 2 kilograms. We do want mass in kilograms, height in meters, and our gravitational acceleration is 9.8 meters per second squared, just like it always is here on Earth. So we are going to plug in these numbers. Calculator. Okay, 2 times 2.1 times 9.8. And our potential energy of our textbook, 41.16 joules relative to the floor. What is its gravitational potential energy relative to your head, assuming you're 1.65 meters tall? So in that case, we are going to use the same mass, the same g, but our height is going to be the difference between the top of our head and the shelf. So 2.1 minus 1.65. Again, the distance that it would have to fall. Same equation. Two times 9.8 times 0.45. 8.82 joules for if the book were to fall essentially on your head. So this would be from the top of the shelf to the floor. This one would be from the top of the shelf onto your head. So, there is an example with gravitational potential energy. And then we have 3 problems for you to do. Right there, 4, 5, and 6. And the very last part of section 1 is elastic potential. When the string of the bow is pulled, work is done on the bow, storing energy in it. If you choose the system to be the bow, the arrow, and earth, then you increase the energy of the system. When the string and arrow are released, energy is changed into kinetic energy. The stored energy in the pulled string is called elastic potential. Elastic potential energy is often stored in rubber balls, rubber bands, slingshots, and trampolines. Anything that can be stretched or compressed has some elastic potential energy in it. Alright, that is all of section 1 from chapter 11.